I would like to show you a map of the city of Königsberg drawn in 1651. Here, you can see how the Pregel River flows through the city. In order to connect the parts of the city located on opposite river banks or the islands in the middle of the river, 7 bridges were constructed. These bridges became the subject of tourists' attention, who would try to devise a path to go across all of the bridges only once. Why don't we try to find one of these paths ourselves? Let's say we start here on the lower shore and take this bridge to the central island with 5 bridges. Next, we can cross the bridge over to the other island and then take the bridge to the bank opposite the one we started on. Here, we take one of the bridges back to the central island and then cross back to the side of the river we started on before returning to the island with 3 bridges. However, once you get here, you become stuck. There are no more bridges that connect to this island that you have not already traveled across, yet there is still a bridge here that has not been traversed. How about you give it a try? Pause the video here and see if you can come up with a route where you cross each bridge only once. Did you find a solution? If not, that's okay. Let's use some mathematical techniques to help us find a path. This problem attracted the attention of Leonhard Euler, the famous mathematician who defined Euler's number. He also is credited with being one of the first people to use graph theory with his solution to the 7 bridges of Königsberg problem. First, he wanted a simplified model of the problem. The only parts of this map of interest to us are the land masses and the bridges, so we can get rid of the streets and buildings from the map. We also do not care about the relative sizes, shapes, or locations of the land and bridges, so we can create a new map of the problem that looks like this. Here, I use these rectangles to represent the land masses, the ones at the top and bottom being the 2 river banks and the 2 in the middle being the islands sitting in the river. I have used lines to represent the bridges connecting the various parts of the city. I would also like to introduce some new terminology when discussing this model. Let's call this representation of the problem a graph. This may not be the kind of graph you are used to from algebra class, where you used a Cartesian plane, but is rather the kind of graph referred to in graph theory. These kinds of graphs consist of vertices and edges. In our case, we are using the land masses as vertices and the bridges connecting them as edges. We are also going to borrow from graph theory what is called the degree of a vertex. A vertex's degree is how many edges are connected to it. For example, this vertex we have here representing a riverbank has 3 bridges, or as graph theorists will call it, edges connecting to it, which makes the degree of this vertex 3. We can now fill in the degrees of the rest of the vertices as follows. Now that we have this terminology, we can begin to analyze the problem from the perspective of graph theory. But first, I want to show you a different graph to illustrate a couple more points. Let's say that we have this vertex somewhere in the graph and that we did not choose to start at this vertex. In order to traverse both of the edges connected to this vertex, we are going to have to come from some other vertex to this one by traveling along one of the edges and continue on to whatever vertex is connected to the other edge. However, if we add another edge to this vertex, we would have to end the path at this vertex because there would be no other edges to travel away from this vertex. This demonstrates that, except for the start and end vertices in our path, all the vertices will have to have an even degree in order for there to be an edge to travel away from the vertex after traveling to the vertex by one of the edges. Now that we know that the odd degree vertices will have to be the endpoints of our path, let us return to our graphical representation of Königsberg. Now we can see why we had such difficulty in constructing a path in which we only travel across each edge once. All of the vertices in our graph are an odd degree, so all of the vertices would have to serve as either starting points or ending points for the path we are looking to make. Since we can only have one starting vertex and one ending vertex, the other 2 vertices will always be connected by an edge that will not be traveled in our path. This is the solution Euler came up with in 1736. Killing the tourism industry of Königsberg with mathematics. However, due to these 2 bridges being destroyed in the bombing of Königsberg in World War II, a path is now possible to traverse each bridge only once. But if you want the authentic experience of struggling to find a path for the original 7 bridges, you can visit this model located here outside the Gene Polisini Center at the Rochester Institute of Technology.